Hello world, welcome to the school. In the previous video of the series, we discussed what data structures were and looked at one of the most basic ones, the arrays, by briefly analyzing how easy it is to access, insert, delete, and search an element. Today, we're going to talk about linked lists. How do these work? Well, a linked list is made up of nodes where each node has some data and a pointer to the next node, forming a link, hence the name. On a higher level, a node will contain some data, along with another node which will contain some data, and another node which will contain some data, and another node. You see where I'm going with this one? Recursion. Linked lists are recursive data structures. Let's go back to their link representation and clear out some terminology. The head is where a linked list begins, and a tail is where it ends. It's very possible that each node can be its own linked list. Another perspective for linked lists being recursive in nature. Let's look at how these can be represented in C. A node of a linked list of integers can be represented with a struct, like so. You can see the recursive nature in its type definition as well. The next field of the node is a pointer to the same type. It might feel weird, but for the compiler, it doesn't matter as long as it can determine the size of the type. All pointers are of the same size, irrespective of the type of data they're pointing to. So the next field will be 8 bytes on my machine. And this never-ending looking structure isn't really a problem. And a linked list would normally just contain one node marking the beginning of the list. How does a linked list perform with respect to those props? Let's find out. To access the sixth element of a linked list, we start from the head, go forward 5 times, and access the data part of the node. Compared to array's arithmetic equation to obtain the address of the value we're interested in, this is worse. Insertion? It's super easy to insert a node at the start of the linked list, as all you do is make the new node point to the existing head node, and make the new node the head of the list. You'd still have to traverse the list if you were to insert a new node anywhere in the middle or at the end of the list. But once you're there, you just need to alter where the nodes point to and not deal with shifting things over. Similar behavior for deletion, where deleting the head node is super easy, but traversal and making nodes point to the right things is still required if you want to delete a node that's not the first one. Searching, as you might have already imagined, isn't that great. In fact, worse than arrays as a binary search is not possible due to the fact that you can't easily jump to an arbitrary position in a linked list. You will have to take the path of the pointers. Let's summarize the performance, and to keep things simple for insert and delete, let's just consider doing those operations at the head. With that, we have bad access, good insert, good delete, and not so good search. Let's talk about the traits with respect to arrays. Linked lists achieve easy insert and delete, but lose fast random access. Additionally, each node will need to carry a pointer to the next node, eating up some space. For 4 integers, the size of the array will be 4 times 4, equaling 16 bytes. The size of the linked list will be at least 16 plus 4 pointers, where each pointer would be an additional 8 bytes, resulting in 48 bytes. I plan on putting the implementations of these structures in a separate playlist. That's all for this one. Thanks for watching.